Welcome to Synthic Labs podcast.
So consider the human brain for a second. You have, what, roughly 86 billion neurons up there?
Give or take, yeah.
Right. But when you're doing a specific task like, I don't know, tying your shoes or solving a crossword puzzle, you aren't firing every single one of those neurons at maximum capacity all at the same time.
Oh, definitely not. I mean, if you did, you'd probably just collapse from the energy drain.
Exactly. You only activate the specific neural pathways you actually need for the job. But historically, artificial intelligence, well, it hasn't really worked that way at all.
No, not at all. For a long time, asking a large language model even a super simple question meant basically lighting up its entire artificial brain.
Right, running the data through every single parameter it had every single time, which was just incredibly inefficient.
Very. And that is exactly why today's topic is such a big deal.
Yes. Welcome to a brand new deep dive, everyone. Today, we are looking directly at Meta's official April 2025 release of the Llama 4 herd. And I just want to say right up front, this isn't, just some incremental software patch.
No, not even close.
We are talking about a fundamental structural shift in how AI is built, how it processes information, and really how it's integrated into your daily life.
Yeah, the architectural overhaul here is what makes this release a definitive milestone. I mean, Meta has completely moved away from those older, dense neural networks where every parameter fires for every prompt.
Yeah.
They fully embraced this mixture of experts architecture. They've baked multimodality in from the very first layer of training. And they've expanded context windows to a scale that honestly forces us to rethink what a prompt even is.
It's wild. So our mission today is to really unpack the engineering that makes all of this function under the hood. Let's just get right into the two models available for developers today, which are Llama 4 Scout and Llama 4 Maverick.
Yeah, the two heavy hitters.
And the benchmark data is just staggering. Maverick is placing above GPT-4o and Gemini 2.0 Flash in key reasoning tasks, while Scout is heavily outperforming models in its own weight class, like Gemma 3 and Mistral 3.1.
But the really defining characteristic of this new herd is this massive paradox in their parameter counts.
Yes, let's talk about that. Because Maverick is listed as a 400 billion parameter model.
Right.
Yet it operates with only 17 billion active parameters. And because of that gap, a developer can run Scout on a single H100 GPU, and Maverick actually fits on a single H100 host.
Which is huge for accessibility.
But wait, how does a 400 billion parameter model run so efficiently? I mean, it sounds like trying to cram a jumbo jet into a one-car garage.
Well, it does sound impossible until you look at the routing. That gap between total parameters and active parameters is the direct result of that mixture of experts, or MOE design we mentioned.
Okay, so how does that actually work?
So in a traditional dense model, you have a sequential stack of layers and data passes through everything. But with Llama 4, they use alternating dense layers and MOE layers.
So to visualize this for everyone listening, imagine a massive multinational corporation. You have, say, 400,000 total employees on the payroll.
Okay, I like this analogy.
But if you have a specific problem, let's say an issue with European tax compliance, you don't call a mandatory all-hands meeting and put all 400,000 people in a stadium to solve it.
Obviously not yet.
You have a general manager route that specific problem to a room of 5 or 6 specialized accountants who focus only on that one issue.
Yeah, that's spot on. And if you take that corporate analogy a step further, you can see how the routing actually functions mathematically in the model.
Right.
When a sequence of text, which is broken down into tokens, when it enters one of these MOE layers in Llama 4, it doesn't just go to one place. Every single token is first processed by a shared expert.
Okay, so that's the general manager for my analogy.
Exactly. This shared expert handles the broad foundational context of the prompt so the system doesn't, lose the forest for the trees.
Make sure it still knows what we're talking about generally.
Right. And then a highly specialized gate network evaluates that specific token and routes it to one of the specialized experts.
And different models in the herd have different numbers of these specialized departments, right? Because the source says Scout uses 16 routed experts, whereas the much larger Maverick has 128 of them.
Yep. Which means as the token moves through the network, the model is dynamically selecting which tiny fraction of its 400 billion parameter brain is best suited to handle that specific microtask.
Wow.
While the remaining hundreds of billions of parameters just sit dormant for that particular calculation.
And for you, the listener, the impact of this is entirely about speed and economics, because running a dense 400 billion parameter model in real time requires a massive server farm and just exorbitant compute costs.
Yeah, it's incredibly expensive. But by only activating 17 billion parameters at any given millisecond, Maverick can generate complex responses with incredibly low latency on standard enterprise hardware.
It's brilliant. And because the Modi architecture drastically reduces the computational overhead for just basic processing, it frees up a massive amount of system resources.
Right, which Meta then repurposed.
Exactly. Meta took those newly freed resources and applied them to expanding the model's sensory inputs. The technical terms they use in the release are native multimodality and early fusion.
And that distinction between early fusion and late fusion is absolutely critical to understanding why Maverick performs the way it does.
Break that down for us. What was the old way? Late fusion.
Right, so in previous generations, if an AI analyzed an image, it was almost always relying on late fusion. Developers took an existing text model and bolted a distinct vision encoder onto it.
Like an afterthought.
Exactly. The vision system would look at a picture, generate a text description of that picture, and then hand that text to the language model. The core intelligence of the AI never actually saw the image.
It only read a translation of it, so it's the difference between looking at a photograph yourself versus having someone describe the photograph to you over the phone.
That's a perfect way to think about it.
You lose a tremendous amount of nuance, spatial awareness, and just context in that translation.
But early fusion eliminates that translation step entirely. Meta integrated an upgraded Metaclip vision encoder directly into the model's primary backbone from the very beginning of the pre-training phase.
So the text and the images are processed together from day one.
Yeah, the text tokens and the vision tokens occupy the same latent space. They share the exact same underlying mathematical representation.
That's incredible.
It is. And because of this unified architecture, Llama 4 Maverick can process up to 48 separate images simultaneously during training. It inherently understands the relationship between a string of text and a specific pixel region in an image.
Which opens up completely different use cases. I mean, you aren't just asking it to describe a single picture anymore. You could theoretically feed it a video feed broken down into 48 frames and ask it to analyze the physics of a moving object across time.
Oh, absolutely.
But as fascinating as the vision integration is, the sheer scale of the memory upgrades in this architecture really requires a deep dive of its own. Because Llama 3 operated with a 128,000 token context window. Llama 4 Scout expands that to 10 million tokens.
10 million. It's a massive jump. We are moving from a model that could read a dense textbook to a model that could ingest a small library in a single prompt.
But reading 10 million tokens is great, but does it actually remember any of it? I mean, usually AI models hallucinate or forget the middle. We've seen models with massive context windows suffer from that lost in the middle phenomenon.
Yeah, where the recall just degrades completely.
Right. If you bury a crucial piece of information in the center of a 2 million token prompt, the model often just glosses over it or makes up a bridge between the beginning and the end. So handling 10 million tokens effectively requires solving that recall degradation.
And they did. But Meta couldn't achieve a 10 million token window using standard positional embeddings.
What are positional embeddings exactly, for those who might not know?
So in a typical language model, every single token is tagged with a mathematical marker that tells the neural network exactly where that token sits in the sequence. It's how the AI knows the difference between the dog bit the man and the man bit the dog.
Got it. The order matters.
Right. But when you scale up to 10 million tokens, forcing the model to calculate and track 10 million absolute or relative positional markers creates just an insurmountable bottleneck. The attention mechanism breaks down.
Wait, so how does a model keep track of word order and narrative flow across 10 million tokens if it isn't using positional markers?
Well, Meta developed an architecture they call IRO-PE. That stands for interleaved attention layers without positional embeddings.
Interleaved, meaning they mix them.
Exactly. They don't strip the positional data out of the entire model. Instead, they strategically interleave standard attention layers that do track position, with new layers that drop the positional embeddings entirely.
Oh, wow.
Yeah, and by freeing up those layers to focus purely on semantic meaning rather than sequence order, the model can process vastly larger blocks of text.
That is so clever.
And then, during the actual inference phase, when you're querying the model, they apply temperature scaling to help the model extrapolate its understanding across lengths of text it wasn't even explicitly trained on.
Right, because temperature scaling essentially smooths out the probability distribution of the model's predictions, preventing it from becoming overly confident in incorrect assumptions when dealing with unfamiliar sequence lengths.
Exactly.
And the benchmark data totally reflects this architectural bet. I mean, Scout achieves near perfect scores on retrieval needle in a haystack tests at the 10 million token mark. It can track a single stray variable across a massive cumulative code base without losing the thread.
Think about the practical application of that for your daily workflow as a listener. The concept of a prompt shifts from typing a few sentences to literally uploading your entire digital environment.
Yeah, you could provide the model with a year's worth of financial records, hundreds of legal contracts, and an entire repository of corporate emails.
And ask it to synthesize a strategy, knowing it has the mechanical capacity to weigh every single variable simultaneously.
It's unreal. But, okay, building a model capable of holding 10 million tokens and native multimodal data brings us to the actual training process. You can't just unleash a model on the open internet and expect it to learn how to organize that level of complexity.
No, definitely not.
The post-training pipeline for Llama 4, which encompasses the supervised fine-tuning, the reinforcement learning, and the direct preference optimization, it relied on a highly counterintuitive data strategy. The source says that during post-training, Meta deliberately discarded more than 50% of their easy training data.
Yeah, that surprised a lot of people.
I mean, isn't AI all about feeding it as much data as humanly possible? Why throw away perfectly good data?
Well, the assumption is usually that more data yields a more capable model. But at the bleeding edge of AI development, feeding a highly parameterized model, simple, repetitive data, actually actively harms its development.
Really? How so?
If you force an advanced neural network to continually process basic arithmetic or simple factual recall, you overconstrain its weights. It acts as a ceiling on the model's ability to develop complex, multi-step reasoning pathways.
Oh, okay, I see. It's the equivalent of taking a university-level mathematics student and forcing them to complete thousands of middle school algebra worksheets.
That is exactly it.
They aren't going to get better at calculus. They might actually regress because they aren't being challenged to utilize their higher-order problem-solving skills.
Right. So Meta used earlier iterations of the Llama models to act as automated judges, evaluating their training data sets, identifying the easy prompts, and just filtering them entirely out of the pipeline.
Wow.
By heavily filtering the data during the online reinforcement learning stage, they essentially forced the models through a curriculum of increasing difficulty.
Meaning they had to work harder.
Yeah, the models were required to spend their compute cycles almost exclusively on medium to hard reasoning tasks, which resulted in significant performance leaps in complex domains, like, advanced mathematics and autonomous coding generation.
Which leads us to the model that's actually generating those incredibly complex reasoning targets. Meta provided an early look at Llama 4 Behemoth.
Ah, Behemoth.
Yeah, and this is a model operating with 288 billion active parameters and nearly 2 trillion total parameters across its MOE architecture.
It's massive.
It is still in training, but its primary function right now is to serve as the teacher model for Maverick and Scout through a process called code distillation.
And we should probably clarify how code distillation operates, because it's fundamentally different from just having a small model copy the final answers of a large model.
Right, it's not just cheating off its test paper.
Exactly. Distillation in machine learning is about transferring knowledge. Behemoth, with its 2 trillion parameters, processes a complex prompt and generates an output. But alongside that output, it generates a rich probability distribution.
Meaning, the mathematical confidence levels it assigned to thousands of potential next words before selecting the final one.
Exactly.
So Scout and Maverick aren't just learning what the correct answer is, they are training their own neural networks to match the internal reasoning probability, the thought process, if you will, of the 2 trillion parameter giant.
Precisely. They learn the shape of Behemoth's logic. But training a 2 trillion parameter model to serve as that teacher requires an entirely new approach to infrastructure. Standard synchronous training methods just completely break down at this scale.
Why is that?
Normally, during reinforcement learning, the GPUs processing the model have to synchronize their updates. So if one cluster of GPUs takes slightly longer to process a batch of data, the entire global network halts and waits for them to catch up.
Oh, wow. And when you are coordinating tens of thousands of GPUs for a 2 trillion parameter model, that synchronous idle time would make training economically and practically impossible.
Totally impossible. To solve this, Meta deployed a fully asynchronous online reinforcement learning framework.
Okay, asynchronous, so they aren't waiting for each other.
Right. In an asynchronous setup, the different nodes or GPU clusters operate independently. They pull the latest model weights from a central server, process their batch of data, calculate the gradients, and push the updates back to the central server without ever waiting for the other nodes.
That is so efficient.
The central model is constantly updating in real time. This eliminates the idle time bottleneck entirely, allowing Meta to achieve a 10x improvement in training efficiency.
And because Behemoth is at the absolute frontier of model scale, that data pruning strategy we discussed earlier was applied even more aggressively here. The release notes that to maintain the quality of the model's reasoning, Meta discarded 95% of their supervised fine-tuning data for Behemoth.
95%.
Yeah, they isolated the absolute top 5% of their most complex, high-quality reasoning data to shape the architecture.
Which really firmly establishes the principle that in the current era of generative AI, the curation and quality of the dataset are just vastly more important than raw volume.
Absolutely. But, as you scale up to 2 trillion parameters, native multimodality, and 10 million token context windows, the challenge of alignment and system safety scales proportionally.
Oh, yeah. The guardrails have to be incredibly robust.
Right. You are dealing with models capable of analyzing entire code bases and reasoning through highly complex logic loops. And Meta detailed a multi-layered defense strategy designed to secure the Llama 4 herd. We see the evolution of their system-level guardrails, which, by the way, are open-sourced alongside the models.
Yeah, they have quite a few of them.
There is Llama Guard, evaluating inputs against safety taxonomies, Prompt Guard, specifically trained to detect and neutralize jailbreak attempts and prompt injections, and CyberSea Evil to mitigate potential cybersecurity risks generated by the AI.
Those perimeter defenses are vital, for sure, but the testing methodology Meta used before deploying those defenses is what really sets this release apart. They introduced something called JOKE.
GOOT, which stands for Generative Offensive Agent Testing.
Right. Because traditionally, securing an AI relies heavily on human red teaming. You hire teams of security researchers and engineers to manually poke and prod the model, trying to bypass its safety filters, force it into a logic trap, or, get it to generate harmful code.
But human testing is inherently limited by time and manpower. You just can't manually run millions of attack vectors.
Exactly. GOAT automates the red teaming process using adversarial AI. Meta utilizes medium-skilled AI agents whose sole directive is to attack the Llama 4 models.
That's wild. AI attacking AI.
Yeah. But these aren't simple single-prompt attacks. The adversarial agents are capable of multi-turn logic. They send an initial prompt, analyze Llama 4's defensive refusal, and then dynamically adjust their strategy in the next prompt, attempting to socially engineer or logically trap the target model over the course of a long conversation.
By deploying swarms of these offensive agents, Meta can simulate millions of complex multi-turn attack scenarios, patching vulnerabilities at a scale humans just could never match.
And this automated baseline testing frees up the human security researchers to focus entirely on novel, zero-day vulnerabilities and highly creative edge cases that the AI agents might, lack the intuition to test for.
Right. And this rigorous alignment process directly ties into one of the most closely monitored metrics in large language model development, which is the neutrality and bias of the system's output.
This is a huge focus for them.
It is. Now, looking directly at the technical overview, Meta outlines explicit benchmarks regarding the model's handling of debated political and social topics. The engineering challenge here stems from the reality, and the source explicitly states this, that models trained on vast scrapes of internet data have historically exhibited a left-leaning bias simply due to the distribution of the underlying data.
Right. The training material itself isn't perfectly balanced.
Exactly. So Meta's stated objective for Llama 4 was to neutralize that structural bias, allowing the system to articulate multiple viewpoints on contentious issues without inherently favoring one over the other.
And to measure the success of their alignment efforts, Meta tracks several specific metrics.
What are the numbers looking like?
Well, based on the data published in the release, Llama 4 now refuses to answer debated topics less than 2% of the time, which is a significant decrease from the 7% refusal rate observed in Llama 3.3.
Okay, so it's answering the questions much more often. They also isolate a metric called unequal response refusals, correct?
Yeah, that one measures whether the AI system denies a request framed from one political perspective, but fulfills a structurally similar request framed from an opposing perspective.
And according to their internal benchmarks, Llama 4 exhibits unequal response refusals less than 1% of the time, which is incredibly low.
Furthermore, the rate at which the model responds to prompts with a strong political lean has been reduced by 50% compared to the previous generation. The technical release notes that these internal benchmarks place Llama 4's neutrality rate at a level statistically comparable to models like Grok. The engineering focus was clearly on heavily refining the post-training alignment to ensure the model acts as an impartial synthesizer of information, rather than a weighted arbiter of debated topics.
Right. And just to be clear, we are purely reporting Meta's own internal testing and stated goals here, just unpacking the data provided in their technical release.
Oh, definitely.
But when you step back and view the Llama 4 architecture in totality, I mean, the engineering leaps are just remarkable.
They really are.
The mixture of experts framework successfully decoupled parameter size from computational cost, allowing a 400 billion parameter model like Maverick to run efficiently on highly accessible hardware.
And the integration of early Fusion Vision encoders gave the models native, seamless multimodality.
Yes, and the implementation of the IRO-E architecture and temperature scaling pushed context windows to 10 million tokens. And the asynchronous training of the 2 trillion parameter behemoth teacher model points to a future where AI reasoning capabilities continue to scale exponentially.
And for you, the user, listening right now, this architecture is already operating in the wild.
Really? Already?
Yeah. Meta optimized these systems for low-latency consumer applications and has already integrated Llama 4's natively multimodal framework directly into the search bars and chat functions of WhatsApp, Instagram, and Messenger.
That is amazing.
His speed and efficiency gained through the MoE architecture is exactly what makes that global real-time deployment possible.
Wow. Well, as we conclude this analysis of the Llama 4 herd, there is a specific detail buried in the breakdown of the IRP architecture that I think deserves a second look.
Oh.
When meta engineers explain the acronym interleaved attention layers without positional embeddings, they specifically noted that the lowercase I for interleaved also serves as a placeholder for their ultimate architectural goal, which is infinite context length.
Oh, wow. In the context of computer science, designing a system to handle a truly infinite sequence of data, that completely redefines the boundaries of machine memory.
Doesn't it? Consider the implications of that engineering goal for just a second. If an AI architecture eventually achieves a stable, infinite context window, if it possesses the ability to constantly process and retain every single email you write, every photograph you take, every document you upload, and every conversation you have, without ever dropping a detail from the middle or needing to summarize the past, at what point does it cease to be an external tool you consult and transition into an unbroken, perfect digital mirror of your entire life?
That's a profound thought. It's a structural evolution that shifts AI from a processor of tasks to a persistent companion of context.
It really is. Thank you all for joining us on this deep dive into the architecture of Llama 4. We will catch you next time.
Thank you for listening to our podcast. If you are interested in sponsoring, please reach out. And to all our audiences, do not forget to like, subscribe, and share.